Hello, Fusion fans. Dr. Matt Moynihan here. I'm going to do my top 10 innovations for nuclear fusion as a field. So what is an innovation? So this is a little bit different than the lectures of the past, which were on approaches, a specific fusion approach. I want to talk about some of the cool engineering, plasma, and science tricks that are enabling fusion to move forward. And I'm drawing this list from the entire field. And then I put them together in a top 10 list because, hey, everybody likes top 10 lists. And because, so the criteria for my ranking is if the approach has more of an impact, it gets higher on the list. So number 10 is going to be an innovation that only applies to a narrow portion of the fusion field. And number 1 is going to be a cross-cutting, huge innovation that I think will really lead to a big step change across all the approaches and all the companies and all the university teams. So without further ado, let's do the top 10 lists of innovations for nuclear fusion. Number 10, microfluidics for target mass manufacturing. So I'm putting this as number 10 because it only applies to the ICF or IFE approach. If you know ICF or IFE, you've got your driver, which is your laser system. Usually, sometimes it can be something else. And you've got your target. That's where you have your fusion fuel in a little pellet that will get compressed either directly, indirectly, or through some other approach, fast ignition or something else. But essentially, you have to have a little pellet that you can shoot and implode and get it to fuse. And those pellets have to be made mass manufactured in a cheap way and put into your reactor in a repeatable, sensible manner over and over and over again. And this is a huge problem. I think the targets are a bigger problem than the driver. And I don't think I'm alone in saying that. We have to get these targets very precisely made, and they have to be very, very cheap. So there is one whole field of technology that applies here, and that's a microfluidic technology. Because the targets are fluid, they start as fluid, and they are created via a foaming process and then filled with cryogenic fusion fuel. Microfluidics offers many different platforms for doing each of the steps that are now done in batch processes. If you're a chemical engineer, you understand the difference between batches of things where they basically process a bucket of stuff, move it to the next station, process it again. Microfluidics moves it to a continuous one-off type thing. So you have one target that moves through a fluid system from station to station and is processed. So for instance, you can form the double shell, then you can foam it up, then you can fill it, then you can freeze it, then you can do quality assurance, and then you can deliver it. So microfluidics is a great way to do that. But since it only applies to IFE, I'm putting it as number 10 on my list. Okay, number 9, RF heating of electrons only. This was an innovation from Sam Cohen's lab at Princeton University, and actually can trace its roots back further to the development of the Rotamac at Flinders University by Ewan Jones in the 1980s. Essentially, plasma is a cool fluid where you have big fat ions and really small electrons. The difference in mass is roughly 1,800 to 3,200, depending on if it's a D or D2. So you can apply a electric field that will only move the electrons if you apply it at the right frequency. The ions are too big and fat to move. The electrons will move. So this allows you to do some cool stuff like create a current in the plasma directly by applying this EMF field at the right frequency. And of course, if you had a current, then you would draw in the positive ions and you form a plasma structure. And you can keep doing that and driving it by continuously applying this field. So the Rotamac is essentially creating a plasma structure with this effect and then maintaining and heating it with the same effect. But it could be applied to a lot of other approaches. I could see it applied to tokamak accelerators and possibly some of the other approaches, mirrors maybe. So that's why I'm putting it there at number 9. Okay, number 8, decoherence of instabilities. So this is a very interesting walk down a plasma theory lane. If in a plasma, you have frequencies. There are frequencies for all the plasma motion. And the alphane frequency is a good example of that. So if the plasma has the same velocity in all places, the frequencies are the same. And what that does is it allows instabilities to grow quickly. For example, the interchange instability or the kink instability or the sausage instability. So the team that really has proven this approach out well is the flowing pinch team at the University of Washington and Zap Energy. Essentially, what they've done is they've created a flowing pinch with different velocities in different places. And if you have different velocities, you have different fundamental plasma frequencies, which, if they're not the same, they're decoherent. It suppresses the growth of instabilities, you see, because if the frequencies were all the same, they would all kind of pile up on each other and the instability would grow. So I hope I'm explaining that well. Decoherence of instabilities is a way to suppress plasma instabilities in any given fusion approach. I mean, you're kind of limited by some factors. You can't apply it to every approach, but in many approaches, it's one possible way to stabilize your plasma by suppressing these instabilities. And it has the most value in the pinch, but it's also been applied to tokamaks. And I think it could be applied to other approaches like stellarations and mirrors, and there may have probably has been work done in that area. But I'm putting it on the list because it's a really great way to suppress some instabilities, and it has a broad impact on many of the MCF approaches. Okay, number 7, traveling wave tube. So this is more of a paper concept. I don't know how many traveling wave tubes have actually been built. There may be some. I haven't done a literature search on this. But essentially what it is, it's a energy capture technology. When you have a fusion event, you have a hot helium nucleus that comes off at 3 million EV, 3 million volts. And if you the traveling wave tube works by passing that helium atom through a tube that's surrounded by a coil of wire. And the voltage that ion is creating is essentially creating a voltage wake behind it. And that wake will draw current, will basically force electrons to move in the wire. And so you can create a current directly from a fusion byproduct really efficiently. So the traveling wave tube is a concept, I should say it's a concept for efficiently capturing electricity from a fusion event. And I'm putting it on the list because of the cross-cutting places it could be used, but I'm also keeping it high on the list because I don't think it's very proven. I think it's a concept, and as far as I know, it hasn't been tested extensively in the fusion space. But it is something that I think people should pursue, and it's a cool innovation. Okay, number 6, gas-based lasers. This was an approach developed by the Naval Research Laboratory starting in 2000 with the KRF and ARF laser system. So when you think of a laser, the conventional laser, you think of a block of neodymium doped glass, for example. That's your lasing medium. And you pump in current using flash lamps or some other approach, and it causes the medium to form a laser light that's all the same and coherent and going in one direction. So that's a conventional laser, and the laser light goes through glasses and other lenses and things to get focused and hit the target. Now, the NRL developed the Nike and so the KRF laser and the ARF laser, and the medium there is gas. It's an electron gas laser. So it's very different. It's a fundamentally different kind of laser. Essentially, the medium is a bunch of gas that you put energy in. You can flash in electricity, and the gas will cycle from a high energy state to a low energy state as a chemical, and it will cycle back and forth, and it will produce laser light. And because it's a gas-based laser, it's much more efficient for transferring the energy from electricity to laser light. And it also doesn't heat up as quickly. So you can do high repetition shots. In fact, the ARF laser has been shot at many hertz over many, many hours, just bang, 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 shot, 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 which is incredible. That's incredible because the Omega system can't do anything even close to that. Neither can NIF. NIF, I think, shoots about once a day, I think. And the Omega system shoots maybe 3 or 4 times a day. In fact, the fastest that Omega could shoot is about every 45 minutes because they need time for the glass to cool off. And they're now talking about active cooling of the glass. Meanwhile, the Naval Research Laboratory has a laser system that can shoot at high rep rates. So it's much more interesting. Okay, number 5, linear transform technology. This is a pulse power technology. So we're getting towards the end of the list now, and we're getting to technologies that have many more cross-cutting applicability across fusion. So pulse power is a problem that everybody has. Most people have. Helion, TAE, Zap Energy, Tokamak Energy, and Commonwealth all have these pulse power systems. Omega has a pulse power system. NIF is a pulse power system. Sandia is a pulse power system. So it's a problem. It's a common problem. And the workhorse of a pulse powered system is generally the Marx generator. I say generally because there's also the supercapacitors that are commonly used too. But the Marx generator has been around since 1920. And the way it works is, for those who don't know, it's a series of capacitors that are first charged up in parallel. So you charge them up in parallel and they build up a voltage across the plates. And then you flip a switch and you put them in series. So basically a bunch of little voltages are then added together to make one giant tidal wave of voltage. And then you flip a switch and current flows down the voltage drop and you get a huge amount of current that you can provide to your fusion hardware. That's a pulse power system. I should also mention that JET uses flywheels as well. So there's other options there. But the limitation of a pulse power system has always been the trigger, basically the trigger at the end of the chain. And the speed and throughput of that trigger has kind of been the bottleneck for the entire pulse power Marx generator. The Marx generator. So in 2006, a Russian team invented this LTD technology, which essentially eliminated that problem. So they created these bricks that could be added together using different configurations to create high voltage, high current pulse powered systems. Very interesting technology. It has some limitations. I won't say it's perfect. There are some voltage profiles that you can't get using this kind of thing, but it is of interest to Sandia National Laboratory. In fact, they are proposing that their next version of the Z machine be incorporated with this thing. And I think I'm putting it high on the list because so many different teams need pulse-powered systems. Zap Energy, CT Fusion, Helion, TAE, they all use pulse power. And this LTD technology provides them a new option for how to power their hardware that has some cool characteristics that Marx generators just simply don't have. So it's a cool technology. I think it should get more attention and more development. Okay, we're in the final 4, so the home stretch now. Really cool technologies coming up. So number 4 is direct conversion. This is another energy capture technology, and it's higher on the list because it's been more tested. There's actually been a body of work around this one. So in a nutshell, direct conversion is you take a fusion event, it creates a really high voltage, 3 million MeV helium atom, and you run that into the wall, a metal wall. And what that does is it makes the metal wall sit at a high voltage. Basically, you're holding it at a really high potential energy or high voltage. And that allows current to flow elsewhere in the machine. So basically, it's like a battery where you're fixing the positive end and you're holding it at 3 million volts by taking the byproduct of fusion and then shooting it into the wall and doing it that way. And so this has actually been tested. It was tested for about 10 years at Livermore National Laboratory in the late 70s and early 80s. The people who worked on it was Ralph Moyer. And when they did it, they actually proved a 47% energy conversion efficiency. Now, it's 47% of what was recoverable from the helium atoms. And if you know anything about fusion, you know that most of the power leaves as neutrons. So it's a really interesting technology. I think it should get more attention. Okay, number 3 is magnetic reconnection. That's a really cool way to quickly heat and start up your fusion reactor. A reconnection event is when two magnetic fields combine to become one magnetic field. It only happens in rare situations where the plasma is dense enough to basically perturb the permeability of free space, the permeability of vacuum. Basically, where the charges are so packed together that they actually create like more of a conducting medium that can infect the region of space. So reconnection happens in the sun often. Huge solar flares will reconnect when two solar flares come together. Their fields will combine and become one field. Now, when it happens, a huge amount of energy exits the magnetic field, and a large portion of that, about 80% of it, can go into the plasma as heat. So essentially, it's a way to pull energy from a magnetic field directly into heating the plasma and heating the plasma up to fusion conditions. Really cool idea. Was first seen in tokamaks, I think in the late 90s. It was first tested in tokamaks in JET. And starting in the 2000s, university labs and national laboratories started to reproduce this effect in test setups around the world. So, 2 or 3 dozen test setups have now been built that can study reconnection events, and it was generally done for astrophysical plasmas. Of late, since maybe the last 5 years, Tokamak Energy started doing it to start up their tokamak. Essentially, they have 2 plasma rings, one at the bottom of the machine, one at the top, and then they push them together and they recombine into one magnetic field. And when they do that, some of the heat comes out, the energy comes out of the field as heat. So it's a really fast, simple, quick way to heat your plasma to fusion conditions. And Tokamak Energy has a really great YouTube video about this where they call it compression heating. So reconnection can be applied to other fusion approaches. I'd love to see it happen in accelerators, for example. I'd love to see it in mirrors, for example. There is a fusion rocket company called Helicity Space that's using reconnection as a way to start a fusion rocket up. Essentially, they create jets of plasma that loop together. They pass it through a nozzle, a magnetic nozzle, that compresses the plasma to conditions where reconnection could occur. Reconnection occurs. It heats the plasma up super, super hot to fusion conditions. The plasma fuses, and then it's shot out the back of the rocket as fusion exhaust. Essentially, that's the mechanism for Helicity Space's rocket. So reconnection is a really cool way to heat a plasma and get it up to fusion conditions. It's also a great way to kickstart a fusion reactor, and it applies to many approaches beyond the ones that we've seen, the ones I've already mentioned. I could also see it being applied to plasma structures. You could have 2 loops of plasma, like an FRC and an FRC, and push them together and get the reconnection event. You could see it in TAE's approach. You could see it in Helion's approach. You could also see it maybe applied to CT fusion, although I'm not familiar with their exact geometry for startup. But you could see a scenario where CT fusion could push together 2 rings of plasma to basically do reconnection and heat their plasma. So the reconnection is a really cool innovation, and it applies to almost all the magnetic confinement approaches. And that's why it's number 3 on my list. Okay, number 2 is artificial intelligence for control systems. This is a cross-cutting and exciting new area, and I'm not the only one to point this out. This has been now researched at a variety of different institutions. I think the first example of this was in 2014 through 2017. At TAE, they partnered with Google AI, and Google AI came in and wrote an optometrist algorithm, to try to optimize the performance of their fusion machine. Now, TAE's fusion machine has 131 variables, basically settings or dials or knobs or buttons that you can push to change the behavior of the fusion reactor. And that's a huge variable space, right? I mean, there's like, I don't know, I mean, however many, 131 to the factorial number of operating conditions you can run this machine at. So how do you figure out what the best way to operate your machine is? Now, there's, a variety of ways you can do it. You can model it. You can use some empirical equations. You can do a variety. You can do, infinite number of tests to basically run the machine at every condition you can think of or map out different conditions. TAE partnered with Google to use an AI to basically map out a path to better performance. And now we've seen examples of this at DeepMind. DeepMind partnered with Jet this year. There was a paper that came out where they optimized the performance of Jet using a neural network. And the same thing has been applied to the Omega laser system. There was a PhD student who just finished up this past year, who did a thesis on using artificial intelligence to optimize for shots. Same thing could work at NIF. It could work at Helion. It could work at SAP. It could work at TAE, CT Fusion. A whole variety of different approaches could benefit from this kind of thing. And if you study neural networks or machine learning, hats off to you. I know a little bit about that topic. But the limitation, of course, is the data set. You need really good data to train your models to make your predictions. So you'd have to do this with a limited scope of data, but you get live feedback from the machine itself, and you can even get better feedback from a model. So there's a variety of ways you could do it to avoid this. Now, there's one company in Austin, Texas called Sapient AI. They won an ARPA-E award to study how to optimize different fusion approaches using artificial intelligence. So this is an area of great interest. And I think there's a lot of really great machine learning programmers out there that love fusion and that want to get involved in this topic. And this is one on-ramp for them to get into the field anyway. So yeah, I think it's a great, exciting area. And that's why I'm putting it as number 2 on my list, because it has such a broad set of applicability. Okay, number one, drum roll, please. Number 1 is high temperature superconductivity and magnets that are built from that. I know I may be beating a dead horse here because this is just so celebrated in the field, but it really cannot be understated how important this technology is going to be for fusion. Commonwealth's 20 Tesla magnet made waves back in September of 2021. And the wire that they used for it was 1 to 2,000 amps per square millimeter. That a copper wire is 2 amps per square millimeter. So if you think about it, that wire had the same carrying capacity of current as 1,000 copper wires put together in one thin strand. So it's a huge efficiency boost for moving current from point A to point B in a fusion reactor. So you can think of all kinds of places where such a cable could be applied. And it doesn't even have to be a magnetic confinement approach. It could be a laser approach or an ICF approach or impact fusion or any number of other places where you need a lot of current moved around. Fusion is a power-hungry field. All these machines are power-hungry. They use a ton of current. You could apply that wire just about anywhere. Now, if you wind the wire, you get a magnet. And the magnet that you produce can be a much more compact, higher field magnet that can also run forever. I mean, superconductors, in theory, have no resistance unless they quench. So they could be run for hours, days, weeks, months. And that's just a game changer. And that applies to mirrors, FRCs, plasma structures, pinch approaches could even benefit, tokamaks, stellarators, a whole set of systems can use this HTS wire, which is why I believe fundamentally that the field of superconductivity and the field of fusion are going to be inexorably linked over the next 10 to 15 years. It's a story we've already seen play out in the tokamak community. I mean, essentially like 2009, tokamak energy was founded with that story, but we haven't seen it play out in these other fields. So it's my number one innovation. That's what I'm going with, number one. Hope you enjoyed my list. If you have any feedback, and please feel free to reach out, email me, put them in the comments, and hope you're having a great day. Take care. Bye.